Alright, so this is where we're going to start talking about a standing wave and what a standing wave is, and then look at how to deal with standing waves on strings. So what happens when you have transverse waves moving down a string is that sometimes two transverse waves can interact with one another. The type of wave that causes sound, this is the type of wave that is actually causes sound to be produced by a string instrument. If that interaction is at certain frequencies, you get a pattern of constructive and destructive interference, which actually creates a wave which looks like it is standing on a string. So if we look at a standing wave, there are a few kind of interesting points to point out about a standing wave. The lowest frequency you can have a standing wave looks like this, where you have just one kind of bump, one area where there's a maximum, and then it usually works best if you're controlling or fixing both ends of the string. This is what we would call the fundamental frequency, or the first harmonic. It is the lowest frequency that's going to cause a wave to look like this on a string. So the second frequency is one where you get two bumps. These bumps are actually called antinodes. They're areas of constructive interference. And so the second highest frequency is what we call the second harmonic, or the first overtone. For those of you who are familiar with music, the first overtone is actually an octave higher than the fundamental frequency. So this frequency is twice as big as the first frequency. When we move to the third possible frequency, we now have three antinodes and then two nodes. Nodes are places of destructive interference. And so this frequency is 3 times as big as the fundamental frequency. It's sometimes called the third harmonic or the second overtone. Now we can continue to do this by increasing the frequency to the fourth harmonic, the fifth harmonic, the sixth harmonic, which have 4 antinodes, 5 antinodes, 6 antinodes, respectively. So let's think about the string moving up and down to create a wave. And then to get a standing wave, I must create waves that amplify one another. So this would mean that only this set of frequencies, F1, F2, F3, is going to create the standing wave. So most frequencies will not create standing waves on this string. So we can think of someone pushing a swing, and the only way to amplify that motion is if that person pushing the swing pushes the swing at exactly the right time. Same thing here in a standing wave. The only way that this gets to be amplified is if you have a crest or a trough meeting here at exactly the right time so that it matches the crest or trough from another wave. So if we think about what needs to happen in order for this to be true, wave needs to travel twice the length of the string during the period of the wave. That's because your wave needs to go down and back. So what this means is your period has to be 2L divided by V, the speed. And so your frequency, if you flip that around, should be V over 2L. So this would be the fundamental, the lowest possible frequency. So this is the fundamental or natural frequency. Now if we added this information that each harmonic we multiply by a number n, what we could get is the frequency of the nth harmonic is NV over 2L, where V is the speed of waves on the string and L is the length of the string. So this equation is important because this equation helps us predict the standing waves that will form on a string, or the frequencies that will form a standing wave on a string. Let's do a quick example. Let's say we have the heaviest string in electric guitar, and it gives us the density of that string, and it's stretched with a tension of 226 newtons. The string produces a frequency with the musical note E, which has a frequency of 164.8 hertz, when the entire length is vibrating at its fundamental frequency. And what we want to do is figure out the length of the string. So one thing to point out about instruments like a guitar or a violin or a cello or a viola is that the strings on those instruments are all the same length. So in order to change the frequency those produce, what you're actually changing is both the density of the string and the tension on the string. So really what you're changing in the strings of a guitar or a violin or a cello in order to get the different frequencies is you're changing the speed that a wave moves down the string at its fundamental frequency, or at its maximum length. Now, you can change the length on each string by pushing down on different frets, like on a guitar, and that changes the frequency by changing the length of the string, so it changes the fundamental frequency. So some things that we know the mass to length ratio, 5.28 times 10 to the negative third kilograms per meter. I know the tension, 226 meters, and I know the frequency, 164.8 hertz. I know that we're talking about the fundamental, so n is 1. So one of the first things I probably want to do is figure out what the speed of the waves is on the string, and then I can figure out what the length of the string is. So here's my relationship for speed, and it's a relationship between tension and mass per unit of length. And there's my relationship for frequency and length. So first thing I'm going to do is calculate the speed of waves on the string, and the way I'm going to do that is just substitute those numbers, and I get 206.9 meters per second. What I then know is I know everything in this right-hand equation except L. So I'm going to try to solve it for L. And the way I would solve it for L is to multiply both sides by L, and then divide both sides by Fn. And so now I have enough information that I could solve for L. Substitute in 1 times 206.9, divided by 2 times the fundamental frequency. So I get 0.628 meters is the length of that string. So the main equation for standing waves on strings is this equation. This will predict what frequencies create a standing wave. And this equation is, remember back to waves on a string, the speed of a wave down a string. So we can use that information as well to figure out what's happening with the string.